So here's part B, problem number 5 from the 2013 AB exam. And they've given us this region R, and in part B they want us to write but did not evaluate, and this happens quite a bit in the free response questions on AP exams. They want you to set up an expression but not actually evaluate it, and that saves you a considerable amount of time as long as you catch that phrase in the directions. So we want to write but do not evaluate an integral expression that gives the volume of the solid generated when this entire region is rotated about the horizontal line y equals 4. So y equals 4 would be right here. And so what we're doing is we're taking this region and we're thinking about pulling it off the screen toward us, rotating it about y equals 4, and trying to find the volume of the solid that results. This isn't easy for me to draw. It's not even easy for me to write with the pen that I'm using right now. So I'm not even going to really attempt to draw it. But what I am going to do is I'm going to say we're not going to get a nice three-dimensional solid. We're not going to get a sphere. We're not going to get a cylinder. We're not going to get a cone. We're not going to get something that we have a volume formula for from out of geometry. So just like we did in part A, rather than focusing on the whole entire solid at once, let's focus on one slice. If we have this one slice and we rotate this vertical slice about y equals 4, so if you think about being able to pull this slice off the screen toward you about the line y equals 4, push it back into the screen here and bring it back to where it started, hopefully you can visualize that what we're going to end up with there is something that's round, it's flat, and it has a little hole poked out of the middle, and we're going to call that a washer. So we end up with this washer, and what we want to do to find the volume of the entire solid is we want to first find the volume of the solid generated by just revolving this slice. We've said that that slice is going to generate a washer when we rotate it. Now, to find the volume of this washer, what we're going to need to do is we're going to need to find the area of the face of the washer. So the volume of the washer can be approximated by taking the area of its face and then multiplying by the thickness of it. So to find the area of the face of this, if I redraw the face two-dimensionally, we're looking at an outer circle, we're looking at an inner circle. The area of everything here is going to be the area of the outer circle minus the area of the inner circle. So the area of the face is going to be found by taking pi outer radius squared, and for the outer radius I'm actually going to use a capital R to represent that, the big radius. So pi outer radius squared minus pi times the inner radius squared. So now it's a matter of trying to figure out what big R and little r actually are. So big R, where does it sit within the coordinate plane? Well, this washer is traced out by rotating this vertical slice about that horizontal line. The outer edge of the washer is traced out by this edge of the slice as it rotates about the axis of rotation. So in the coordinate plane, this distance from the axis of rotation to the bottom edge of our slice is going to represent big R. Now that's a vertical dimension from in the coordinate plane, so it's got to be specified by a difference in y values, and we need to make sure we get it so it's positive. So we're going to take the bigger y value, which is always further up in the coordinate plane, and the bigger y value is 4. Right? The axis of rotation has a y value of 4. And then the smaller y value is the y value at the bottom of the slice. Now no matter where we draw the slice, the y value at the bottom of the slice is always on the parabola, and the parabola is defined by f of x. So the big radius is going to be 4 minus f of x. The small radius, well, the hole in the center of the washer is because as we rotate this slice about the axis of rotation, the top edge of the slice does not border the axis of rotation. So we get this little hole that's poked out in the center of the washer, and the inner radius is going to be specified by this vertical dimension, from this y value here to this y value here. So the y value at the top, again, is 4, and then minus the y value at the bottom. Now the y value at the bottom, no matter where we choose to draw the slice within the region, the y value here is at the top of our slice. and the top of our slice has a y value defined by the cosine graph, which is g of x. And so what we can say about the volume of our washer, the expression that we were trying to develop back here, is that the volume of our washer can be found by taking the area of the face, which is pi big R squared. So big R we just specify to be 4 minus f of x. So there's pi big R squared, the area of this outer circle, and then minus the area of the inner circle, and the inner circle has a radius of 4 minus g of x. And then that quantity also has to be squared. This is the area of the face of the washer. If we multiply by the thickness, we're going to have the volume of this washer. Well, the thickness of the washer comes from this dimension on our slice. And that dimension on our slice is some tiny, tiny difference in x values. So we're going to specify it to be delta x. So the thickness of this is going to be delta x. So here's the volume of one washer. What we want to do is we want to find the volume of the entire solid that's generated by rotating r about y equals 4. So if we had a bunch of slices drawn and we generated a bunch of washers and we found each individual washer's volume, we would add all those volumes together to get the volume of the entire solid. We're lucky because the definite integral is going to do most of that work for us. It's going to add together an infinite number of these washers' volumes as long as we toss this expression here for the volume of one washer into our integral. So I'm just going to copy this down into my integral. So I'm looking at pi big R squared. Whoops. That's 4 minus f of x squared minus pi little r, which is 4 minus g of x squared. This is the area of the face of the washer. Now the thickness as specified over here is delta x, but when we put that into an integral, that's going to become our dx, telling us what to integrate with respect to. And then the limits of integration have to be values of x. They have to match the differential here, and they have to be all x values that slices that we could have potentially drawn within this region range between. Well, the smallest slice is going to have 0 as its x value, and the slice with the biggest x value is going to be over here at an x value of 2. So if we do this integral from 0 to 2, we have just set up an integral that would find the volume of the solid that's described in part B, and we luck out because we don't have to evaluate it.